So as you said, I am now at VTT, where I'm a research professor. Before then, I've been in VTT for 5 years, and before that, I was a chief researcher at British Telecom Research in the UK. So I have a career in applied R&D, if you want. So basically, I'm going to give a relatively short presentation, hopefully, on swarm intelligence as a frugal form of AI. It's just an example of a frugal kind of AI, just the one that I happen to be most familiar with. So basically, I'm sure you're all familiar with the old adage that when all you've got is a hammer, everything looks like a nail. And to a large extent, I think that's where we are with artificial intelligence today. AI has been very much a victim of its own success over the last maybe 2 decades or so. As a result, it has been forced into performing tasks for which it was never intended. An example of these you will hear in everyday news as students using ChatGPT to complete assignments that they should have done by themselves. However, of course, it would be bad if the only effect of the generalization of the use of AI was encouraged intellectual laziness. But because of the disproportionate cost in computational and energy resources that is used by AI, as we've heard in previous presentation, it is considerably worse. And I don't think I have to spell out this other metaphor at this stage. So, could sustainable AI just mean that we should have less of it? Or rather, could it mean that we should look for means to restrict the use of AI to what it's actually uniquely good at? And I insist on uniquely here. What is AI uniquely good at? Well, it usually boils down to detecting well-hidden patterns in very large amounts of data. But part of the problem that we are facing is not about AI itself, but about the fact that it's a very attractive and seductive tool for people who could use other ones in order to tackle the problem they're facing. But because it's very easy to use, it's very easy to use natural language in order to ask a scientific question, even though you would have a better, more efficient answer if you were using a more structured way of finding the solution. It is actually growing at an exponential rate, not so much the AI design and the AI training, but the amount of AI usage that you see in society as a whole. And the point is that being able to do something, and AI can indeed do your math assignment for you, doesn't make you the most efficient at doing it. I mean, you could very well use a hammer to swat a mosquito, but this is not the best way to do it. And if you do it in certain cases, it might even have side effects that you would rather dispense with. And that would not be an issue if the ultimate goal was intelligence by itself. So for instance, if you're trying to create general AI and it takes petawatt hours to do so, well, then so be it. But more often than not, intelligence is not a goal. It is a means to an end. And that end is arguably, and that's my own opinion, adaptive behavior. Now, let me propose you a definition from an alien scientist, a definition of intelligence by an alien scientist. Intelligence is a particular kind of information processing that is leveraged by some biological or artificial entities to produce a flexible response so that their performance remains high when their circumstances change. In nature, of course, everything is a cost-benefit calculation. So intelligence had to evolve on a budget. And our big brains are arguably a huge and risky investment that paid off. Now, some biologists might actually question the fact that we know that it has paid off because in the greater scheme of things, we mammals have only been at the top of the food chain for a relatively short time in the history of life. And furthermore, if you look at other measures of success in biology, like the biomass, we are very far from being the top dog on the planet. We are far behind things like bacteria and arthropods. But the point is that there are other forms of intelligence that can foster good enough adaptive behavior at a fraction of the cost of what our brains consume in terms of power and materials. And one of these is what has come to be known as swarm intelligence. Now, swarms are nothing else than another kind of complex adaptive systems. All brains are complex adaptive systems. Swarms are complex adaptive systems. They're just a different kind of them. The most important distinction between our own information processing method and the one that is used by swarms is arguably that it outsources a substantial part of the information processing to the inanimate world, the physical world. It usually takes the form of capitalizing on a combination of positive and negative feedback in order to identify adaptive solutions to the problem that they're facing in their environment. And one of the best known example is the discovery of the shortest path between 2 points, which forms the basis for what is known as ant colony optimization. So I don't want to go into any details here, but essentially what happens when ants explore the environment is that they're marking it with a chemical substance known as pheromone. And when an ant meets a pheromone marked substrate, it has a tendency to follow that trail. And when it does so, it adds more pheromones. So we have the basic for the positive feedback here. However, there's also a negative feedback, which is like any other volatile chemical, the pheromone evaporates over time. And as a result of this very simple method for marking the environment and detecting the presence of a mark in the environment and the physical chemistry of the interaction between that chemical signal and the substrate, you have the basis for a mechanism whereby the collective, so the hive, is able to discover the shortest path in a maze or in a set of bridges. Now, the point here is that this collective decision is achieved at a negligible cognitive and metabolic cost compared to other forms of information processing. It's just good enough for what it needs to do, which is to find an efficient way of foraging. Now, I wanted to take a short detour here because it has been argued that now that we have moved into a post-AI world, whatever that means, the relevance of swarm intelligence and other forms of intelligence that are found in the natural world that we can use as inspiration for designing artificial intelligence is no longer relevant. And there was even recently one of the most recognizable names in swarm intelligence, whom I will not identify here, but you can probably figure it out if you look it up. He wrote something on his LinkedIn profile that I'm paraphrasing here, but he said something like, if I had known that we would have so much processing power at our fingertips in 2024, I would have joined my colleagues working on neural networks all those years ago instead of swarm intelligence. Now, from my point of view, this is kind of missing the point, because this line of thought is essentially the product of a more is always better fallacy. And this is actually the fallacy that has brought us where we are here, namely at a juncture in the history of our civilization, where we are facing the existential threat that is related to the fact that we are using more energy and raw materials than the planet can provide. So, and that's the reason why we're here discussing sustainability of AI, of other things. So the point is that many applications, and especially in distributed robotics, where I spend most of my time working, is that these applications do not need anthropomorphic AI. They only need a kind of cheap and dirty insect-grade adaptive behavior. So I'm going to give you a short illustration of that using a little demo that involves looking at swarm intelligence in action. It's simulated action because doing it in the real world would require a bigger budget, but that's not an indication that it would not be possible to do it in the real world, and actually we're working on it at VTT and with our partners. So the scenario I'm looking at is a simple exploration and surveillance scenario, because that's one of the low-hanging fruit application, if you want, for swarm intelligence. Let's imagine that we have a swarm of bots, and these could be drones in most of the applications we can think of, but they could also be ground robots or other types of autonomous devices. So this swarm is tasked with achieving and maintaining the best possible situational awareness over a designated region of interest. So that essentially means that they have to explore the environment and then keep it under observation until such time that the operator declares the mission over. So they do this by clearing what is known in military circles as the fog of war. the fog of war is actually a relatively interesting concept. It basically means that you don't know anything about an area in which you've never had eyes, but also if you knew something about a place at some point in time, but you no longer have any ability to observe that area, then you lose this information. This information is no longer accurate, and you might not be able to have good intelligence on that area. So as a result, the fog of war is something that covers the entire environment before you start the mission. But as your sensor devices are moving around and leaving some regions, the fog of war builds up again in this area. Now, as in biological swarm, there are nonlinear cooperative effects in these exploration tasks. So you can think, for instance, at the drone trying to pinpoint the location of something, someone in the woods. And if you know that the drone is there, you can hide behind a tree. And you can do the kind of squirrel thing. And if the drone is going around, you keep getting the tree between you and the observer. And so you're never spotted. But of course, if you have two drones, that is no longer a viable strategy. So that's where the source of comparative effect come from. And finally, in the example I'm going to show, the group coordination between the different members of the swarm is simply a variant of the basic particle swarm optimization algorithm, which means that each unit is accelerating in a direction that is essentially an average between its own individual optimum and the optimum as detected by the entire swarm. So now I'm going to switch to the demo to illustrate this. And I apologize if the movement is a bit jerky. I know that it's going to be quite smooth on my screen, but I have no means to know exactly what you guys are saying, but hopefully it will be good enough. So here we have a number of devices, bots or drones, that are indicated by these red dots. And if I let the system run, they are currently following their kind of individual bias random walk. So they are homogeneously spread in the environment. And as they go, they clear the fog, which is why you see this white cloud starting to break down, and you start to have little gray areas where the fog has been cleared, and where it eventually will build up again, but it takes some time to do so, which reflects the fact that the information was at some point accurate, but no longer is. But if I change some parameter values, and the important thing here is that I can change just one global parameter and completely generate a different behavior, it's going to start having some interesting features. So for instance, if I increase this, the K value, you see that the swarm is beginning to coordinate its activity. And as a result of the cooperative effect that I mentioned, that means that they're able to clear more of the fog in one point when they all concentrate on that area. And now you have this behavior, which I'm not piloting. I'm just piloting in terms of the global parameter value. But you see that the swarm is behaving in an interesting way, alternating between focusing on one point and then breaking up and starting to look for other places to explore. And of course, there's also no reason for this to remain in abstract space like this and having this grayscale representation. But if you think that this swarm is actually a swarm of real UAVs that are trying to keep the area under observation, then you could actually superimpose a map of the actual terrain behind it. And then you will see how this exploration can actually reveal different parts of the area and give you some up-to-date information about them. Even more so, there's nothing that stops me from interacting with the swarm and designating an area where they're not at the moment as one that they should prioritize. So for instance, if I do this, then the swarm will go where my cursor is, and I can direct them to follow me. And when I leave them to their own devices again, they will resume their autonomous behavior. So essentially, I have the building blocks here for a swarm behavior that would be a very successful method of keeping an area under observation and keeping good situational awareness. Furthermore, its short-term behavior is unpredictable, which has all sorts of advantages if you think of surveillance applications. So for instance, if they were following an optimal lawnmower pattern, it would be very easy to anticipate where you can remain undetected. But with this swarm behavior, good luck in trying to achieve the same effect. Now, if I go back to the presentation, I will show you some of the results that you can measure about the performance of the swarm. And I do this for two reasons. One of them is that I think it's important to remind the audience in these presentations that even though I like to show fancy demos, it's also quite important to emphasize that this is not just moving pictures, but that there is some good science behind and some measurable performance gains that you can achieve with them. But also because one of the objections that you often get to this sort of logic is that it's not predictable. Swarms are not predictable. Well, they are very predictable. They're only predictable on a statistical level and not on an individual instantaneous level. And I see that I have to accelerate, but this is my penultimate slide before my conclusion, so we should be fine. So basically what you just see here is that as you've changed the value of a parameter, namely the parameter K I was playing with in the demo so far, you get an increasingly good performance in terms of the ability of the swarm to dissipate the fog of war, but you also reach an optimum. Beyond K equals 3, you start getting less efficient response if you keep increasing that parameter. And you can also show that the value of this optimum varies depending on the size of the swarm. So basically, you can do all sorts of computation here that allows you to predict what is the best parameter values depending on the kind of mission that you are trying to achieve. Now, moving to my concluding remarks. Well, we cannot deny that AI has transformed our relationship with big data. It cannot be stressed enough, as Frédéric said, for instance, that AI is an essential tool for scientific research in the 21st century. We wouldn't have all these nice Webb telescope images without it. And it has proven itself such a powerful tool that we are going through something, an AI gold rush. And the AI gold rush has some implications in terms of the undesirable effect of this. Now, even though there are realistic prospects of reducing the energy use and carbon footprint of AI, we have no guarantee that exponential growth in demand won't dwarf these efficiency gains. So that's something to keep in mind. There is an element of Jevons paradox here. And I don't have time to remind people what Jevons paradox is, but I encourage you to look it up because it's quite a thought-provoking thing. Now, finally, I would like to emphasize that autonomy, adaptivity, and intelligence are not synonyms. So basically, you can get autonomy and adaptivity without intelligence, at least without what we call machine learning. And the example I showed, there is no learning involved. There's just another form of intelligence. And so my conclusion overall would be that we shouldn't always find ourselves more nails because we have a hammer. We should also try sometimes to look for alternative tools to solve the problems that we meet. And I think that will be the end of my presentation. Thank you very much.